We tap an icon on our phone and instantly we know where we are and how to get where we're going. GPS is a seemingly simple, everyday convenience, a ubiquitous tool for navigation that guides billions across the globe. We use it without a second thought, expecting perfect accuracy every single time. This seamless convenience, however, belies an astonishingly intricate technological foundation. What appears effortless is, in fact, a triumph of engineering and scientific understanding operating at the very limits of physics. The precision we rely on demands far more than basic geometry. This underlying technology, for instance, must actively account for the mind-bending effects predicted by Albert Einstein. We're talking about relativistic phenomena like time dilation and the subtle warps in space-time itself. Without these complex calculations, your navigation would quickly fail. Even more surprising to many, GPS was not born from a desire for convenience apps. At its core, the Global Positioning System is a multi-billion-dollar military weapons system, forged in the crucible of Cold War tensions and strategic necessity. Its civilian use was an afterthought. The intense geopolitical anxieties of the Cold War era profoundly spurred the development of precise navigation technologies. Nations urgently sought any advantage that could tip the delicate balance of power. Accurate positioning was paramount for strategic operations. A pivotal moment arrived with the Soviet Union's launch of Sputnik in 1957. This stunning achievement intensified the burgeoning space race and significantly escalated the global arms race. The United States recognized an urgent need to counter this new technological threat. A critical requirement emerged from the U.S. Navy's Polaris submarine program. These submarines carried nuclear missiles and needed incredibly accurate guidance for their payloads to reach distant targets. Precise location at sea was essential for successful deployment. Existing navigation systems of the time, such as the Navy's transit system, had severe limitations. Transit offered infrequent location fixes, was only two-dimensional, and required several minutes for a position calculation. It simply wasn't precise or responsive enough for missile guidance. The military desperately required a system that could provide 24/7, all-weather, three-dimensional location data. Such a capability would offer an unparalleled strategic advantage, transforming everything from troop movements to intelligence gathering. The stakes were incredibly high. Thus, a top-secret initiative named the Navstar GPS project was formally approved in 1973. Its mission was to develop this revolutionary new positioning system, securing America's tactical edge in a world constantly on the brink. The project began in earnest, cloaked in secrecy. The ingenious solution devised was a network of satellites orbiting Earth, forming what we now call a constellation. These specialized satellites circle our planet at an altitude of approximately 20,200 kilometers, constantly broadcasting signals. This high orbit ensures broad coverage. Each satellite continuously broadcasts signals containing two vital pieces of information: its precise orbital position and the exact time the signal was sent. These faint radio waves are the lifeblood of the entire system, carrying critical data across vast distances. The fundamental principle behind GPS location is called trilateration. This method calculates your position by determining your exact distance from multiple known points. In the case of GPS, those known points are the orbiting satellites themselves. Your GPS receiver measures the minute travel time of the signal from each satellite. Knowing the speed of light, it can then accurately calculate the distance to each individual satellite. This forms the basis of all positioning. For this system to work with such astounding accuracy, the timing information must be unbelievably precise. This is why each GPS satellite carries multiple highly precise atomic clocks, far more stable than any clock on Earth's surface. These clocks are the heart of the system. A single satellite tells you that you are somewhere on the surface of a sphere centered on that satellite. Two satellites narrows it down to the intersection of two spheres forming a circle. Three satellites narrow it further to 2 points on Earth. To resolve this ambiguity and determine your precise location, a fourth satellite is crucial. It also allows your receiver to synchronize its own much less accurate internal clock with the highly precise atomic clocks in orbit. This synchronization is critical for accuracy. Therefore, the GPS network effectively acts as the world's largest and most accurate timekeeping device. Its primary function is not just location, but the precise dissemination of time across the globe, enabling a vast array of technologies beyond navigation. Without accounting for Einstein's theories, GPS would utterly fail within minutes. If only Newtonian physics were applied, the system would accumulate errors of approximately 11 kilometers per day. This would render it completely useless for modern navigation. The system relies on the continuous and meticulous application of Einstein's theory of relativity. Both special relativity and general relativity must be precisely factored into every calculation. This isn't theoretical, it's a practical necessity for accuracy. According to special relativity, clocks moving at high speeds relative to an observer tick slower. GPS satellites orbit at incredible speeds, roughly 14,000 kilometers per hour. This speed causes their onboard atomic clocks to slow down slightly. The effect of special relativity means the satellite clocks lose about 7 microseconds per day compared to clocks on Earth. While tiny, this error would accumulate rapidly, throwing off all distance calculations within hours. It's a measurable and critical factor. Then there's general relativity, which states that clocks tick faster in weaker gravitational fields. Because GPS satellites orbit high above Earth, they experience slightly weaker gravity than clocks on our planet's surface. This also impacts their timing. The general relativity effect causes the satellite clocks to gain approximately 45 microseconds per day. So, while special relativity makes them lose time, general relativity makes them gain even more, creating a complex interplay of forces. The net relativistic effect is that satellite clocks, left uncorrected, would run faster by approximately 38 microseconds per day. This is the difference between the 45 microseconds gained and the 7 microseconds lost. It's a significant daily discrepancy. To counteract this, engineers intentionally offset the satellite clocks before launch. They are calibrated to run slightly slower on the ground before being sent into space. This pre-compensation is a testament to the precision required. This deliberate offset ensures that once the satellites achieve their operational orbit, their clocks are in perfect synchronization with ground-based reference clocks. This intricate engineering allows GPS to maintain its astonishing accuracy day after day. GPS stands as a real-world, everyday testament to the validity of Einstein's theories. It constantly demonstrates the effects of space-time warps and time dilation, proving that these complex concepts are not just abstract physics, but practical necessities for modern technology. For years, GPS remained primarily a military tool, its capabilities reserved for strategic defense. The shift towards civilian access was precipitated by a tragic event that highlighted the desperate need for better navigational aids. In 1983, Korean Airlines Flight 007 strayed off course into Soviet airspace and was shot down, killing all 269 passengers and crew. This catastrophic event was attributed in part to a navigational error, exposing the vulnerability of existing civilian systems. In response to this tragedy, President Ronald Reagan made a momentous decision. He declared that the GPS signal would be made available for civilian use once the system was fully operational. This marked a profound shift in the system's purpose. However, even with civilian access, there was a catch. The U.S. military implemented selective availability, intentionally degrading the accuracy of the civilian signal. This limited civilian users to an accuracy of approximately 100 meters, reserving precision for military applications. In a landmark decision in May 2000, President Bill Clinton ordered the disabling of selective availability. This immediate action drastically improved civilian GPS accuracy to a remarkable 5 to 10 meters, transforming its potential overnight. This newfound precision unleashed an unprecedented wave of innovation across countless sectors. It directly enabled in-car navigation systems, revolutionized smartphone capabilities, and became indispensable for precision agriculture. GPS technology fundamentally transformed logistics and supply chain management, optimizing routes and tracking shipments globally. It also became a crucial tool for emergency services, vastly improving response times and coordination. Its impact was truly global. From its secretive origins as a Cold War military weapon, GPS has transformed into an indispensable global utility. It is one of the most powerful and pervasive technologies ever developed, touching nearly every aspect of modern life. This unassuming system powers our modern world in countless, often unseen ways. It guides our cars, tracks our fitness, timestamps financial transactions, and even helps farmers plant crops with unparalleled precision. Its influence is far-reaching and fundamental. Its extraordinary accuracy, which we now take for granted, fundamentally relies on the deepest laws of the universe. Without a meticulous application of Einstein's theory of relativity, GPS simply would not function. It bridges the gap between theoretical physics and daily practicality. GPS stands as a powerful example of the hidden complexities embedded within our everyday technology. It reminds us that behind the simplest convenience often lies a profound tapestry of human ingenuity and scientific discovery, constantly at work, often unnoticed.